All right, I think I'll go ahead and get started. My name is Michael Greenberg, for those of you who haven't been before, and today I'm just going to talk a little bit about working with files. So that'll be both talking about good I/O patterns and also how to store your data in the most efficient way possible. And if anybody ever has any questions at any point, feel free to just blurt it out, message me in chat, and I'll go ahead and try to address those because it's easier to address them as they come up than wait until the end sometimes. All right, so let's start out with kind of a 1,000-mile view here. We're going to talk about why there are so many different storage systems. So we've got our SSDs on each node on the supercomputer. We've got central storage, compute in your home directory. Of course, there's RAM on each node, and the CPUs have caches and registers. So the problem is there are trade-offs here in space, cost, and speed. So even though registers are extremely fast, and registers, these are where you would store variables in your program. For example, if you say, I have X and Y, and I need to do some work with those would probably be stored on the CPU in registers. Registers are very, very fast. Usually a CPU can move stuff around on the registers in one clock cycle, which, there's 3 billion cycles in a second or something like that on modern CPUs. So those are very fast, but they're also very, very expensive. If you had a gigabyte of register space, I'm pretty sure it'd be tens of thousands of dollars. So we can't have all of our memory being that sort of memory. Even though it's fast, we need to consider the fact that there's a huge cost to that kind of speed. And so the next thing we go out to is the caches. So there's 3 caches on modern CPUs. You've got your L1 cache, your L2 cache, and your L3 cache. And each of those is increasing in size and decreasing in speed. So your L1 cache might be a few kilobytes, but it's going to be very, very quick. That's maybe, I think, 2 to 4 clock cycles to move something around in there. And as you go out to L3, the size gets bigger and the speed gets lower. So the reason we have these caches is we can't fit all the data we need to compute on in registers. And so we have to have somewhere to kind of store intermediate data while we're not using that data right there. So once we go off of the CPU die, we get out to the RAM, and that's our memory. It's pretty fast, but it's going to be something like 40 or 80 nanoseconds to get something from RAM. So that's somewhere around 100 clock cycles. So when a program needs to fetch something from RAM, it's going to have to wait quite a while for that to get pulled into the cache where it can access it much more quickly. And once we're beyond memory, we've got our persistent storage. So a hard disk or a solid state drive, something like that, that is even slower to access. That's going to be thousands of clock cycles of waiting if you have to go out to disk and fetch something from there. And of course, we also have network storage. So that's your compute in your home directory. That can be accessed from anywhere on the supercomputer, any node, but it's very, very slow. Getting something from disk is just an incredible amount of clock cycles. It's microseconds, but think about in 1 microsecond, you've got about 1,000 or more clock cycles on most processors. So the reason that we have, I guess, all of these, this hierarchy is so that we can compute fast, essentially. So if I have a data that I'm accessing very frequently, I'm going to want to put that in one of the caches or possibly even the registers if it's small enough. And when we do that, it means that our speed can go up significantly. The reason I bring this up is because we've got a couple types of storage on the supercomputer, a couple file systems. And this kind of gives a good background for why we have each one. So we've got home directories. That's where you get when you first hop onto the supercomputer. We've got compute directories, and this is a big file system. I believe each person gets 20 terabytes, and it's pretty fast, but it's not backed up. So this is that network storage I was talking about. It has very good streaming performance, meaning once you've opened a file and started sending data over the network, that data is going to arrive quickly. But because it's on the network, it still has fairly high latency. So that's home and compute. We also have /temp, which I'll talk about that a little bit later. But this points at the hard drive on each node on the supercomputer. So let me go ahead and share my terminal with you here. And we'll go ahead and take a look at each one of those storage systems. All right, can everybody see this okay?
Yeah, I can see it.
Perfect, thank you. All right, so when I first log into the supercomputer, this is where I get dropped. This is my home directory right here. So again, this is just a network file system in essence. And this is for storing your persistent data. It's pretty small, but it is backed up. So you do things like results that you need for papers, or maybe software that you've compiled in this home directory. But it's not super performant, and it's not very big. You've got about a terabyte there. But if you want a lot of data, you're going to want to go into your compute directory. And this is, as is evident by the name, this is where you want to do your computing. So if you are crunching some data, put it in the compute directory and have the results go into the compute directory. And if you need anything from there backed up, you can just move it over to your home directory after you're done. So compute, it's really big. It's 20 terabytes, but it is not backed up. So make sure if you have anything that you cannot lose to either put it in your home directory or push it up to cloud storage or something along those lines. So again, this compute and that home directory, these are both network file systems. So when I access a file from the compute directory or from the home directory, I have to go from whichever node I'm on over to the storage appliance and ask for that file. And the storage appliance will go ahead and send that file back over the network to whichever node I happen to be on. So as you can imagine, there's quite a bit of latency involved with that. And I'll show you a pretty stark example of that later on. But for now, just keep in mind that whenever you access something in your home directory or your compute directory, you're going over the network to do so. So the other type of storage is /temp. This is local to each node. So you can see what I've got in here. I've got this build, asdf.txt, hhsuite, etc. If I go to a different node, let's say I'll go to login 1 here. You'll see that the contents of /temp are different because it's pointing to a different solid state drive, the solid state drive on login 1 rather than login 2. Make sure I type in my password here right. Oh, good, perfect. What do we got here? Okay, you can see that the contents, just like I was saying before, are different here. So let's go ahead and pop back out. And I'll go ahead and hop back to the presentation here. All right, so we've talked a little bit about this. Just one quick, note to keep in mind. When you're using files, it doesn't really matter the file system. You want to keep your directory listings small. So let's say I have 1 million files that I need to store. One thing I could do, of course, is just dump all of those 1 million files into one directory without any organization or structure. We call that a flat directory structure, and that is bad. The problem is listing files or searching for files in such a directory takes a lot longer than searching in a smaller directory. A much better way to do something like that would be to create a directory, and then within that directory create, say, 1,000 subdirectories, and in each of those subdirectories putting 1,000 of your files. So that's a much less flat directory structure, and each directory listing is going to be of a reasonable size in that case. One extreme example of this is we had a user who was storing millions of files in a single directory. And when he wanted to list the files or try to find a file within that directory, he was having a lot of trouble doing so. And the problem was that the directory cache, which is a little cache that essentially stores the contents of a directory so that you can access those contents quickly. The directory cache was filling up before that huge directory was being listed. So what would happen is he would say ls or whatever it may be, and the directory cache would fill up with, say, half of the contents of that directory, and then it would have to go back out to disk to ask again. And so every time he listed that, it was thrashing the cache. It would fill it all the way up. It wouldn't be enough. It would evict that, fill up again with the next, 100,000 files or whatever it may be. And so this made his performance pretty low. And we had a lot of trouble with backups in addition to that due to that flat directory structure. So if you have a lot of files, make sure to split them up appropriately and make sure that each directory listing has as few children as possible, essentially. So a good rule of thumb is to keep them smaller than about 1,000 immediate children. All right, the way that we access files is also very important in addition to storing them properly. So when one accesses a file, if you read or write in huge chunks, it's going to be a lot easier on the computer than if you do little chunks. So let's say I've got a process and it needs to read from a file, and it does so in 2 reads, 2 big reads, maybe, 4 kilobytes apiece. That's going to be about the most efficient way you can read that file, especially if the access is sequential, because you're only going out there and you're just reading. There's not a lot of seeking. And seeking is once you've opened a file, going, say, 20,000 bytes to the part of the file that you need to grab. So if you can avoid that and just grab the whole file at once or read in big sequential chunks, you're going to be much more efficient in accessing your data. So really the worst way we can access data is randomly seeking around in a file and reading small chunks. So let's say I am going through a file and I want to grab every, say, 1,000th line, but not in the correct order. So maybe I want to grab the 13,000th line, then the 4,000th line, then the 25,000th line. That's going to be very inefficient because we have to open the file, seek to where that data that we want is, and then read that little teeny chunk. That's a very expensive operation. So if you can avoid doing things like that, make sure you do, because that sort of thing can slow down programs significantly. I'm talking orders of magnitude slowdowns. So again, just make sure that you access your files intelligently, in essence. Another thing to be careful of is opening the same file repeatedly. So in this example here, I'm just writing a little bit of data into a file in a loop. So with this top example here, this is bad because each iteration of this loop, I'm opening and closing this file, this myfile.txt. So each time we open and close a file, I have to go over to the storage appliance, tell it, hey, let's open up this file. get the data back or write the data to it, and then close the file. And once I do the next iteration, I have to do the same thing. So that's very inefficient. The better way to do this is open up the file outside of the loop, as you see in this second example right here. So when we do that, all we have to do is go out to the storage appliance, say, hey, I'm going to open up this file for writing, write all of our data, and then tell the storage appliance that we're closing up the file. So that is a huge difference in speed. And I'm going to go ahead and show you that right now because it's pretty absurd just how quick this is. Pop back to my terminal here. Okay. So let's see, what do we got here? Oh, count file. Sure, use that. So the first thing I'm going to do here is I'm going to do this the naive way. So let's say I want to write 10,000 numbers to a file. I'm just going to write I into this file. And what I'll do is I'll go ahead and use this append operator. Let's just say count.text. All right, so once I hit enter, what this is going to do is 10,000 times, it's going to print a number, 1 through 10,000, and it's going to append that to count.text. And what append means in this context is it's going to open up count, it's going to seek to the end of the file, it's going to write there, and then it's going to close that file. So this is going to be 10,000 opens and closes, and you'll see that it's fairly slow. Even though we're writing just a tiny amount of data, something like, several kilobytes, it takes quite a while, and I forgot to time it, of course. That was the whole point. So yeah, we've got around 4 seconds. And again, this is a tiny amount of file. It shouldn't take nearly that long to write that much. So let's go ahead and do this the smart way. We're going to do the exact same thing, but instead of writing it all at once, or all in little pieces and appending it to that file, we're going to do it all at once. So this loop here is just going to echo 1 through 10,000 on new lines each time. And then what we're going to do is we're going to open that file all at once and just pour all of our data in. So let's just call it something else, just so you can see that even though it's a different file, it's going to be way faster. So yeah, as you see here, as promised, we've got a 2 orders of magnitude speed up just by reordering where moving the open and close of the file outside of the loop. So keep this in mind when you're working with files. Just make sure to minimize your opens and closes. That is one of the biggest things that drags down performance on people's applications, is opening files too much and messing around with them. So the principle of this is, when possible, keep your opens and closes of files outside of loops. All right, let's hop back to the presentation here. Okay.
So, Michael, can I ask a question right there?
Yeah, please do.
Suppose that I'm going to open a great big file and I'm going to take one line out of the middle of it or something, edit it, and put it back in. But it's a big file. You're saying be better to read that like all into memory and then do the manipulation and then write it back out to disk again?
Well, in that case, there's really not much to be done, because you're going to have to do quite a bit of seeking anyway. If it's a truly huge file, there's really not much you can do. You've just got to seek, find the thing, and then write it again. But that sort of thing is kind of hard to optimize. Honestly, it's best to, read in from the big file and write out a small file. But when that's not possible, what you're doing, just opening the file and replacing a line is about the best.
Okay. So, okay, thank you.
Yeah, and actually, so Lloyd is a little bit better at file IO type of stuff. I'll go ahead and give it to him to go ahead and discuss that.
Okay. You guys hear me all right?
I can hear you.
Okay, good. So,
Yeah, I can hear you.
Dr. Hart, the biggest issue with these kinds of things happens mostly when you're doing a large amount of it. So if you're just doing one kind of operation, I don't think the effect is going to be very significant. But the issue that occurs most often is when someone needs to write a whole lot of data, but they write it in small chunks. Then exactly how you do it makes a big difference. You know, if you were only writing, say, a few bytes, to use Michael's example, I don't think you would see much of an effect because none of them would be doing very much. The whole group of operations would be pretty quick no matter what. Michael gave his example. He was doing 10,000 iterations. So I don't know that the effect is going to be very big in your case. The ideal scenario there essentially is to open the file, seek to where you want, write the changes, and then close it. And that's all it should have to do. You don't have to do anything in particular, but it's mostly a question of at large scales, what is the average IO size?
Okay.
So if you can make that
So if I have
if you can make
Go
the
ahead.
average larger, then the overhead of doing things like opens, seeks, writes, and closes is mitigated by the fact that you have fewer operations total.
So I don't know if this is a specific enough question to be useful, but if I have a big file, but it still fits into memory, and I want to do a relative, and edit a relatively small part of it, but maybe that's a few thousand edits, then in that case, I'm much better off to just read it into memory, and then do all the edits, and then write it back out. Is that the right idea?
That's probably true, especially if you can do the edits in roughly sequential order within the file. Then most of that should be handled by the caching algorithms of the file system anyway.
Okay. Okay, thank you.
Yeah, so basically the principle is like if you have to do a lot of writes and a lot of reads, just buffer them. But yeah, like Lloyd said, if it's just one file or one operation, it's usually not a huge deal. And yeah, the same principle applies with files. So if I have a lot of little files, I'm going to have probably a lot worse performance than if I have a few big files. So one of the problems is that opening and closing files does have quite a bit of overhead, especially on network file systems. The problem is also that metadata isn't free. So for every file, I have to know where on disk it's stored. I have to know the last modified time. I have to know its name. And that data does take up space. And performance for that reason, and because closes and opens are so expensive, is a lot better if you can put all of your data into very few files and work with it like that. So let me show you guys a little example here. So what have I got here? All right, so I've got this many small files directory. This has, I think, 10,000 little files, each one with a random number in it. Actually, let's just make sure that's true. So yeah, 10,000 files. And then I have this few large files that has 100. And each of these files in many small files has one line. So for example, with one, it's just an integer like all of these guys. So there are 10,000 of those little integers in many small files. And in few large files, we have 100 files, each with 100 lines of random numbers. So we have the same amount of data in many small files and few large files, but they take up quite a bit different amount of space. Say many small files. So yeah, you see that on disk we've got 500 kilobytes for a few large files, and for many small files, which again is 10,000 files rather than 100, it's taking up 45 megabytes. So that's a pretty surprising difference considering that, again, it's the same amount of data. But it's just because each block on disk can only store one file. So if we've got a 4 kilobyte block size, even if my file only takes up 10 bytes, on disk it's still going to take up 4 kilobytes, which is hugely painful for this kind of thing if you have, say, millions of tiny little files. They're going to take up a huge amount of space compared to the actual amount of data that they hold. I also have this, what did I say, one large file. Yeah, this has 10,000 lines of random numbers, and it's a tenth of the size of this few large files directory. So let's go ahead and check out some performance. I've got this little executable here. It's called average. And what it does is I give it a directory name or a file name. And if it's a file name, it goes ahead and averages all of the lines in that file. And if it's a directory, it goes through every file within that directory recursively and gets the total, I guess the average of all of those files, each line of every file, I suppose. So if I say average of many small files, okay, let's go ahead and time this. It's going to go through each of those files, each of those 10,000 files. It's going to count everything up, and it's going to get an average. So because I used $random, which ranges from, I believe, 1 to 32,000 something, and it's a uniform distribution, so I get the 16,000 here. But you'll see that it took 2 seconds to do that. Even though the averaging operation is super cheap, especially in a compiled program like this, it takes a lot of time to access each of those files. So if I do that with the few large files, you see again, we get about a 2 orders of magnitude increase in performance. Then let's do it with one large file here. Just so you guys can see how stark a difference it is. So even though few large files was only 100, you can see that that took most of the time for the program to open and close those. So like I was saying, aggregating all of your data into as few files as possible can be a huge performance boon for you, especially if you're going to be doing a lot of accessing of whatever data you have stored in those files.
So what if our files are really large, like 250 gigabytes? Is it still faster to find random lines in a 250 gigabyte file than like a 10 gigabyte file?
I guess that depends on how the data is structured. If you have some knowledge of like how it should be split up, then maybe grepping for a random line in a 250 gigabyte file is going to be a lot slower than a 10 gigabyte file. But if you need all of the data and you need it sequentially, then a big file is almost always going to win. But in a case like that, there is a point of diminishing return.
Makes sense. Thanks.
Yeah, no problem. All right, let's pop back to the presentation here. Okay, so I was talking about how the block size means that small files don't get stored efficiently. This is just a quick example of that. So right here, maybe I have a 2 kilobyte file and it's in a 4 kilobyte block. So this is wasted space. Nobody else can use that. you can see that these big files also have wasted space, but they're all going to be right at the end. So if I have a 15 kilobyte file, yeah, there's going to be a kilobyte of wasted space at the end because it's going to take up 4 blocks. But that's a lot more efficient than storing a bunch of, say, 3 kilobyte files. And one of the ways that we can solve this is using tar. So basically what this does is it takes all of those files and just puts them into one file. It has some information, some metadata to, I guess, tell you how the files are sorted, essentially. So it retains the structure of whatever directory you've tarred up, but it's really just a single file, and so it stores much more efficiently. So let's go ahead and take a look at that real quick. Another thing I should mention is that there's really two ways of storing tar balls. You can zip them up or you can not zip them up. And that's going to be dependent on the type of data. So let's just go ahead and show the size of these two right here. So this many small files.tar.gz, this is a zipped up version of the many small files directory, and you can see that it's way, way, way smaller. So I've saved myself a ton of space just by tarring that up. And tarring is seriously super easy. So let's say that I want to tar up this few large files right here. I'm going to say C, Z, because I want it zipped up, and then F is going to be the file name. Let's call it few large files.tar.gz, and then few large files. Boom, zipped up. Let's see how much space we saved there. So it wasn't as significant this time because few large files is composed of larger files. But you can see that we still have quite a bit of space. So we can look at that. We can also do the same thing. We can check out what's in this tar file here. Oh, yeah. Make sure that we actually type in the right thing. So yeah, this shows us the structure that we've got in there. It's also really easy to unzip this if we wanted. Just say tar xf, whatever the tarball name is. Whoops. Keep relying on tab complete. There we go. Okay, so these tar balls, the other useful thing about them is that when I want to transfer a bunch of data to a node, if I can do that with one file rather than with many files, it can make things much more efficient. So let me hop on back to the presentation. Are there any questions about tarballs? I know this is kind of a weird thing, I suppose.
So, Michael, question, in that last example, was your savings coming because you were zipping, or was your saving coming because you were recovering the unused block space at the end of every file?
It was both. Maybe I should actually, you know what, let's just do it without zipping so you can see that we get benefits from both of those. So zipping only does help sometimes. So if I have very incompressible data, for example, if it's like images like pings, that's not going to be worth compressing. But if it's text like I've got here, it's going to help quite a bit. Wow, interesting. So the zipping up hurt us this time. I don't know why that is. Interesting.
Hey, Michael, for very small files, the overhead of the compression mapping that lets you decompress it can be a problem. That effect is really only true for very, very small files, though.
Okay, yeah, that makes sense. Yeah. So yeah, if they're
maybe try it on the.
Oh yeah.
But still, these large files, the few large files, they were still like 100 lines or something, right? With 100 numbers in them. I don't remember.
Yeah.
So anyway, it's interesting that the compression didn't save us some, because they're just text, so they ought to compress well. But I don't have a good feel for how big a file ought to be before the zipping helps.
Yeah. I'm thinking I did something wrong actually, because that's too small. The 512. Yep. Okay. Okay. That makes a little more sense.
That makes more sense.
Yeah.
That makes more sense.
Yeah. I was like 512. There's no way all that's fitting in there. Okay. Yeah. Yeah. So zipping does help here, but yeah, if they truly were teeny little files and there weren't very many of them, zipping could be more overhead than it's worth. But yeah, most of the time,
Why
yeah.
don't you try that? You've got it right there. Give it a whirl.
Huh.
That looks like the same mistake somehow.
Yeah, indeed. So what did I do wrong here?
It's 512 again.
Huh. Clearly I'm doing something wrong. Okay, there it is. Don't know why that was. But yeah, I think that would only be, I think the gzipped one would only not help if it was like very few files, like maybe 100 files that are like a few bytes each.
Oh, because the tar happens first, and so then essentially you have a bigger text file, and then so once it's a bigger text file, then it'll zip fine.
Yeah, yeah, exactly. All right.
Okay, thanks.
Yeah.
Sorry, I don't mean to sidetrack you. I'm just curious.
No, this is good stuff. Perfect. Okay, so this, using /temp, we're going to go ahead and talk quite a bit about this because this helps a lot of people get their work going quite a bit faster. So like I was saying, /temp, that points to the solid state drive or the hard disk on whichever node you happen to be computing on. So if I submit a job and it's only a single node and I want to be messing with the file a lot, it's going to be a lot faster to move that over to temp once, do all of my computing on it, and then move whatever results back into my compute or home directory. So because the data is on the node, we don't have to go and ask the storage system over the network for a file each time we open and close it. So let's go ahead and just, I'm going to show you like how incredible this really is, because it makes things much, much quicker. So let's see. So I've got this average guy. Make sure I can access this from wherever. Okay, perfect. So let's pop into temp here. And actually, you know what? Before we do that, let's just do a reminder real quick of how slow this many small files things was. Average many small files. So I think it was like 2 seconds. Yeah, around 2 seconds. So if I pop over to temp, and here I'm going to go ahead and unpack the many small files tarball. So now I've got many small files. Now that I'm in temp, I'm on that local node. I'm still going to be opening and closing 10,000 files, but because we don't have to go over the network to do that, it's going to be like way faster. Average many small files. Boom. Okay, yep. And what do we got here? That's like, what, 1/10 of a second rather than 2 seconds. So about an order of magnitude speed up just by doing our computing out of temp. So usually temp is what you would use after you've exhausted all of your other options. Obviously, the best way to do this is to just use the appropriate big files. But if you can't control your program that you're using, for example, say you downloaded some software and you've got to run it, you can use /temp as kind of a band-aid over that, in essence. Let's pop back to the presentation here. So really the best type of performance you can get if you aren't able to aggregate all of your data into one file or very few files is to tar up everything. So say you have 100 million images, or that's a lot, I guess. Say you have 1 million images that you want to run some machine learning algorithm on. The best way to do that is obviously to aggregate those images into some sort of file. But say you're using somebody else's program and they require you to have these in individual files. The best way to do that is going to be tarring up all of those images into one tarball, moving that over to your node, whatever compute node you happen to be on, doing all of your number crunching on those things, on those images in /temp, and then putting your results back either to compute or your home directory. So one of the most extreme offenders that we've seen for like bad file IO patterns is Gaussian. So back in the day, we had a lot of problems with Gaussian, and it wasn't the fault of the users. It was just a very poor IO profile, essentially. So we had to instruct people to kind of be, I guess, handle Gaussian with rubber gloves. So what we would make them do is have their checkpoint files, they call them read-write files. It's just some file that Gaussian abuses. We had to have them put those in /temp because it would bog the whole storage system down for everybody on the supercomputer. And it was so bad that we actually had a little program, Gaussian Hunter Killer, that would track down Gaussian programs that got out of control. So we made a special script called gbatch to kind of automate this process of moving the checkpoint and read-write files over to /temp before doing the number crunching on it. So sometimes you can't really do much about bad file IO patterns, and that's when temp can really, I guess, come into its own, I suppose. So yeah, I would strongly recommend using /temp if you're dealing with a lot of little files, or if you have to do, say, a lot of random seeking in several files. All right, so just a quick overview.
Michael, I have to.
Yeah.
Can I ask just 2 questions related to this?
Of course.
The first question is, if my program is doing a lot of writing, but the writing's pretty sequential and it comes in big chunks, is there still significant savings having it write to temp because it's on the local node, or is that, I'm just wondering if I'm slowing myself down when I don't do that?
Well, if it's sequential and they're big chunks, it's not going to make too much of a difference.
Okay. My second question is kind of a best practices or what you would like us to do. Kind of a question. Suppose that, I have a script that copies everything over to temp. It runs for a day, and then it copies a few files back to compute or back to my home directory. And suppose I don't delete all that junk that I left on temp. Tell me, is that how bad that is?
It's not terrible. We do ask that you clean up after yourself, but I believe we have cron jobs that run on all of the compute nodes to clean people's leftover data up. So it's certainly not a disaster if you don't clean it up, but it'd be nice.
So here's a story that's kind of old, but I had a bunch of scripts that I would run, and it would copy everything over to temp. So it would CD to temp, it would, you know, copy a bunch of stuff, CD to temp, run a bunch of stuff, and then it would copy stuff back, and then it would do like an RM star inside of temp, right?
Yeah.
But okay, maybe I'm going to make a fool of myself here, but one of the CDs failed once, and that RM star ran in my home.
Oh, yeah, that's
So
painful.
that kind of made me nervous about deleting stuff when I was doing it in a script instead of live, if that makes sense.
Yeah, yeah. That's that's a dangerous game. So what I tend to do for that kind of thing is I use mktemp. So if I need a temp directory, I say mktemp, I grab the output of that. And at the end of the job, I just say rm-r, you know, the name of that temp directory. So if it fails, I mean, it fails, but it's not going to ruin anything unless I left the variable empty or something like that.
Yeah. So is mktemp, is that something on the supercomputer? Is that standard Unix? That's not familiar to me.
Oh, I don't know that it's standard Unix, but every Linux I've ever been on has it. Um,
Oh wow, my Mac knows it. I didn't know it existed.
oh yeah, I'll
Interesting.
bet it's a Unix thing then, I guess. Yeah, so that will make a temporary file. If you do mktemp-d, that gives you a directory. And that's
And so
actually,
you just
oh yeah.
so your best practice is just to do that and somehow store the name, and then when you do the RM, just use the name again.
Yeah, yeah, exactly. Just be careful with your
So how do I? Okay, so when I do the make, how do I capture the name in the same, you know, when I do the make?
So what I usually do is I just say, just a sec.
Oh, Brandon just told me in the chat. Okay,
Okay,
never mind, I got it.
perfect.
Thanks.
Yeah, yeah, that's exactly it. Beautiful. So yeah, this will give me a directory. Yeah. So one other thing to keep in mind when you're using /temp is if you have, say, a job array or just a bunch of jobs that are going to be running wherever it may be, you want to make sure that they don't clobber each other's stuff. So if I launch a job array of 10 jobs, I'm definitely going to want to use that mktemp because if I don't, I might be overwriting data from other members of that job array. All right, so that's it as far as our main content here. But yeah, just the things to keep in mind are big files are better, small files are bad. You want to try to aggregate data as much as you can. The most efficient way to read and write data is to do it sequentially. So if I have a huge array, I want to just write it out all at once if I'm going to be writing that, rather than doing it piecewise. Or if I'm reading, I would like to read in all the data I'm going to use rather than jumping around. And maybe the biggest thing to keep in mind is in /temp. Well, I guess if you access a file from compute or home, you're already going over the network to get that file. So if you're going to be accessing it multiple times or something, you're going to want to probably just move that over to /temp anyway, because the expensive part is moving the data from compute or your home directory to the node that you're doing your work on. And another thing to keep in mind, both for cleanliness and performance, is using tar. So if you've got archival data, you want to tar it up, or even if you have data that you're working with that's in a bunch of small files, you're going to want to use tar to work with that kind of data. And again, just like we were talking about, use /temp as kind of a band-aid over poor I/O patterns. Alrighty, any questions or comments? Oh, yes. Ryan actually just reminded me to remind everybody that /temp only has so much space. So this is a single solid state drive, and it's shared between everybody on that node. So if you have a 2 terabyte file or something, don't try copying it over to /temp. This would be for things like, you know, a 10 gigabyte file or 1,020 megabyte files that you've got to be working with. All right.
Michael,
Yeah.
one more question. What shell are you running?
Oh, this is just bash, but
Okay.
Z shell is better.
Okay. Okay. Thank you.
Yeah, no problem. All right. Any other questions? If not, we have a little bit of time for one of our bonus topics. I think what I'd like to talk about is rclone. And rclone, we're not going to be able to go through all of the setup type of stuff today, but we have a little page on our website on setting it up, and I will link that when we post this video on our YouTube channel. So rclone, essentially what it does is it's kind of like rsync, but for cloud storage. So if I want to move something from the supercomputer up to, say, Box or Google Drive or whatever it may be, I can use rclone to do that. And this is useful because sometimes, well, not sometimes, it's always annoying to have to move a file from the supercomputer to your computer just so that you can upload it to Box or wherever you want to upload it. So rclone is like a, oh yeah, perfect. So Ryan just in the chat linked the instructions on setting up rclone. So yeah, rclone, it's a way to access your cloud storage from the command line, essentially. And once you've got it set up, it's super slick. So I'll just go ahead and show you guys just a little bit of an example of how it works. Oh, can I share the right thing though? Oh, yes, I can. I was just... So let's say I want to see all of the stuff that I've got stored on Box. Oh, first thing we have to do is module load rclone, sensibly enough. So this is just saying list the directories that I've got on Box. And I honestly don't remember what I've got there. So let's see, I suppose. Oh, well, it looks like my refresh token has expired. So I'm going to have to, at some point, go ahead and refresh that token there. So I think what happened here is I haven't used this in 60 days. And so that authentication token that Box gave me has expired. So that's one thing to keep in mind. You're going to want to use Box fairly regularly. So what I'll do is, let me see, I think I've got it set up on another computer here. Let me just make sure that's true. Okay, perfect. Looks like I've got it. Go ahead and share this terminal with everybody. Okay. So let's see what I've got on Box here. I've got, yeah, this all makes, well, I don't know what all this stuff is. Cool. Anyway, so I can look at data here. So let's go ahead and see what I've got. Actually, I don't know. I don't know what I've got in here, so I don't want to be like showing everybody. But you can copy stuff up to box. So let's see. Let's say I want to do one of these random movie files, move it up to box. I can just say rclone copy the name of the file, and I'll need to make sure to quote that. Box. So now I'm going to have that that movie file or whatever it is up in box, and I would show you that, but I don't want everybody seeing like my credentials because I don't, and not necessarily the credentials, but I don't remember what I have in box. But yeah, rclone, awesome way to manipulate all of your data from the supercomputer. So one example use case for this is if you've got something in your compute directory that's just too big to put in your home directory, but you really do want it backed up. rclone is a great way to do that. You can just move it on up to cloud storage, and the added benefit is that if it's archival data, you can free up your storage on the supercomputer for more important stuff. So any questions about just the general principle of using rclone? I don't know if I'm going to go into too much detail on its usage today because we do have that page about it. But any questions about just how it works generally? All right, if not, and if there's no more questions, I'll go ahead. Oh, chunker, yes. So one thing to keep in mind with Box is that the files are limited to 32 gigabytes. So Box has because it has this limit, we use a chunker overlay is what we call it. So you set up your Box authentication essentially. And once you've got Box set up, you'll create another backend that you could call, Box Chunker or whatever it may be. And what that'll do is if you have big files, say you have a 100 gigabyte file, it'll go ahead and split that file up into whatever size you specify. So say I specify 30 gigabyte chunks because Box limits me to 32 gigabytes. It will transparently split that file up, store it on Box, and then if you ever want to pull it back down with rclone, it will automatically put the file back together for you. So this is all on that rclone page that we've got on the website. So for more details, just go ahead and hit that up. But keep in mind that if you are wanting to put big files on Box, you're going to want to use that chunker overlay. All right, any questions about anything that we've talked about thus far? All right, if not, I'll go ahead and let you guys go. Thank you everybody for watching, and we hope to see you next week at our next seminar.